No questions? All good or like everything is bad?
So, I've seen the lecture yesterday. So, in starting, you have shown the circuit of ST and SBT both. And when you're deriving the things, you only shown ST, not SBT.
Correct. Yes.
Because if you show SBT, the voltage will be reset to zero. Why?
Okay. So no, I mean, I agree with what you are saying that we did not consider SBT while analysis, but will that make any difference?
But if short circuit the SBT, okay, ST will be open. Okay, so
Right. So
I was thinking,
yeah. Right. So ST and SBT are complementary to each other. So it would have been a problem if there was a capacitor connected on the other end of the switch. What I mean by that, I mean, his question is, if you recall, we did not, I said that there is a switch here, SBT. Like this. And while trying to figure out the capacitor voltage, right? So we did not consider the effect of SBT at all, right? But in not doing that, did we incur any error? No. Why? Because ultimately when when ST is on, SBT is off and vice versa, right? So in a way, the voltage at this node is not affected by the what I should not say voltage at this node. When I say voltage at this node is not affected whether SBT exists or doesn't exist, right? Now it would have been different if I had a capacitor here. If I had a memory element here, then the effect of SBT becomes important, right? Because when I open this switch, if SBT is not present, then the voltage across this capacitor will there will be a residual voltage across the capacitor the next time I turn on ST, right? The voltage, the ST, the voltage that will be dumped on this capacitor will not be only dependent on the input, it will be also dependent on the voltage, accrued voltage on the red capacitor. And if I have SBT, then I am shunting it out. Instead of if I do not have SBT, that memory effect will come, right? So if I have a capacitor there and I do not consider SBT, then it would have been a problem. Okay. But yeah, it's a good question.
about the ST that is
So by the way, I mean, there is naturally you can think, right? So now if you put this capacitor, the analysis becomes even more complicated, right? So the set of equations will simply increase, right? So, and there are some weird thing happens if you put this capacitor there. I mean, will not have time to go into that in this course, but what I will do, I mean, after I go through, today also there will be some more math. After that, what we'll do is I will show you a ways of looking at the circuit in a slightly different way where the math will be reduced, but under certain specific constraints that you'll be able to figure out how the circuit evolves. Right now, we are kind of taking everything into account, right? We are not neglecting anything. The only neglect that we have done is probably at the very end of the analysis, we have said that RC time constant is much more than T, right? So, T on, right? So TS, right? My RC time constant is much more than TS. That is the only constant we did in order to simplify the big expression that we got. But that big expression is valid regardless of any constraint, right? And as you will see, I mean, after today's class, hopefully, I mean, from the next class, what we'll try to see is that if we put some realistic constraints, then the analysis can be thought of in a slightly different way, which will be much more useful, right? Okay, so bear with me for this class. Okay, so if we recall, so what we had done is we were trying to figure out the transfer function, or rather, I should not say transfer function, I should say the response at the output V naught t if the input is e to the power j omega naught t or e to the power j omega t, right? And we saw that, what did we see? We saw that if this s of t is periodic, and so on. Then we saw that your input is e to the power j omega naught t. After doing bulk of analysis, we saw that if we are observing the output at this falling edges of s of t, right? So I am observing the output there or there and so on. Then we could figure that your V naught t will be, or the envelope of V naught t, that is h j omega t on, will be that big expression. Can someone shout it out? I remember the first one, which is the easier one, 1 plus j omega RC. And then there will be something, right? Something in the numerator, something in the denominator. There will be 1 minus something, 1 minus something. What is that something? So in the denominator, there will be some e to the power something, e to the power real term. The real term is the same. Yeah. T on by RC. No. The real, it was e to the power minus T on over RC. Then there is another complex exponential. So here it will be j omega T on. Here it will be j omega ts. Okay. And we did a bunch of simplifications at the end of the previous at the end of the class in the previous lecture. We did the condition when omega is equal to omega s, right? So let's start off with from there and see what if omega equal to omega s plus delta omega, right? Okay. So for omega equal to omega s plus delta omega, what will you get? So by the way, just for the sake of continuity, let me also write it. So V naught T or V naught not T, V naught T on is e to the power j omega t times h of, or rather h of j omega t on times h of j omega t on, right? And needless to say, this is equal to V naught of T on plus NTS, right? Sorry, I made a mistake here. So this is your h of j omega T on is equal to h of j omega T on plus Ts, right? The mistake that I was making is it will not, V naught need not necessarily be periodic. V naught will be periodic if there is a certain relationship between omega and omega s, right? Because the periodicity holds for this. If you multiply this with some other signal which does not share the periodicity of the input, then the output need not be periodic. Okay? So that is an important consideration. Okay, so now we are saying that what happens if omega is in the vicinity of omega s, right? So, and obviously delta omega is much less than omega s. That is the assumption. So what do we get? We'll, similar to previous times, we'll do the simplification of this term. So h of j omega s plus delta omega T on is 1 by, so the denominator, I will drop the 1 because omega RC is, again, the idea is omega RC is much greater than T on, or rather TS. So which means that I can, the denominator I can have j omega s plus delta omega RC, right? In the denominator here, I can have e to the power minus T on over RC to the power minus j omega s plus delta omega ts. Again, in the numerator, minus t on over RC times minus j omega s plus delta omega t on. Okay. Now I can start the simplification, further simplification. Since delta omega is much less than omega s, I can basically say this is j omega s RC times 1 minus e power minus t on over RC times this omega s times ts is 2 pi. So effectively it becomes e power minus j delta omega ts. And here it becomes or minus j omega s t on. And t on is basically ts by n, right? I mean, so I can say ts by n times it is minus j delta omega t on. And ts omega s ts is 2 pi. So this becomes 2 pi over n. Correct? Okay. So now we were doing the case where n equal to 4 so far, right? So let's continue that. If n equal to 4, then this approximately becomes 1 by SRC. The denominator I can kind of simplify. This becomes 1 minus T on over RC minus J delta omega TS, right? And the numerator is, so this guy becomes minus J, correct? If n equal to 4, so I get 1 plus J e power minus T on over RC times e power minus J delta omega T on. And like before, because this is plus and this is J, I can effectively say that this is close to 1 without making, without incurring too much error, because T on is much lesser than RC, delta omega is much lesser than omega s. So I can effectively say that exponential term in the numerator is close to 1, right? So because, I mean, one of the reasons we can say is because we're doing 1 plus and there is a j associated with it. Right? Had it been 1 minus and j wouldn't have been there, then we would have to be careful. In that, for example, the new denominator looks to be the similar thing, but we have something different. Okay, this becomes 1 by T on over RC plus J delta omega TS. I multiply with RC by T on in the denominator. So, yes. Right, correct. 1 plus J. Thank you. So I multiply with RC over T on in the numerator, I mean in the denominator. So I get 1 plus J. Sorry. So this becomes T on over RC, right? Okay. So this one cancels. Again, T on times omega s is basically 1 by J omega s Ts by n, Ts by 4. The 4 goes on top times 1 plus J by 1 plus J Ts by T on is n delta omega in RC. So this becomes, this is 2 pi. So 2 by J pi 1 plus J times 1 by, so this is H of S plus delta omega T on. Okay, fine. This is pure math, nothing, pure algebra. So So now what is this telling us? It's basically telling us if delta omega equal to 0, that is omega equal to omega s, we are getting a finite value, right? Which doesn't seem to be a filtered value of an RC circuit. What I mean is that if I have a continuous time filter, and if RC is much greater than Ts, which means in this case 1 over omega s, and the input is at e to the power j omega st, what do you expect at the output approximately? Do you expect a finite value or a very, value close to 0? So what does this constraint tell you? Omega s to be much greater than time period, RC to be much greater than the time period, will be very slow, right? Which means what? The capacitor is holding on to the charge, right? Which means the capacitor voltage is not moving. So incrementally, the capacitor is shorted if the capacitor voltage is not moving, right? So I can say incrementally, this current is e to the power j omega st by r, approximately, correct? Because the capacitor voltage is not changing incrementally. And now this current is flowing into the capacitor, and it will create a voltage of 1 by j omega c times the current, right? So you are going to get a voltage across the capacitor, which is inversely proportional to RC, basically inversely proportional to omega RC. And if omega RC is much greater than 1, right? So naturally, you are going to get a severely attenuated version of the input across the capacitor, right? For this particular frequency, omega s to be much greater than the time period. Okay, it's a continuous time filter. Same thing, just we put a switch here. The same circuit, we just put a switch here. And now we are again observing the voltage across the capacitor at omega s. What are we seeing? We are seeing that there is no attenuation, isn't it? So the magnitude of this is very close to 1, isn't it? It's 2 root 2 over pi, effectively, the magnitude. So 2 times root 2 is 2.8 divided by 3.1, 8.9 also. Hardly any attenuation, right? And that all that we did was use the same RC filter, which was totally attenuating the input. We just put a switch in between and observing the voltage across the same capacitor. And we see that there is absolutely no attenuation of the voltage. Okay. That is the power of LPTV systems. It is an example of an LPTV system where you can basically, you can almost mimic the effect of whatever was happening around DC at any higher frequencies, right? When you do analog circuits, what is one of the challenges that we face? At higher frequency, there is attenuation. There is attenuation, there is phase lag, this, that, right? What this technique is telling you is that there seems to be a way out where you just put a switch, you vary the way the circuit is behaving, and in a periodic way. It seems like the DC gain of this circuit, which was supposed to be 1, right? The DC gain of an RC filter is 1, right? We are almost getting that DC gain at an arbitrarily high frequency omega s, right? Just by putting a switch. And that obviously you can assume this will have far-reaching consequences, because you can mimic a low frequency thing, good things at a low frequency at a higher frequency. Okay. So, and needless to say, once you know that this has such a big effect, everybody jumps into, the research community essentially jumps into figuring things out, that how can I use this in various ways. So this is still an evolving field, right? Not everything has been uncovered. Okay, and the example that I showed you here is with omega equal to omega s plus delta omega. But the same thing you can do for omega equal to 2 omega s plus delta omega, 3 omega s plus delta omega, and so on, right? But interestingly, what happens if I do for omega s equal to 4, assuming n equal to 4, right? So n equal to 4, can you find out quickly what will be j 4 omega s t on? Do it and let me know. So if omega s, omega equal to 4 omega s, what is, if omega equal to 4 omega s, then what is omega s t on? It's 2 pi, right? No, 4 omega s. See, input is omega s, 4 omega s, right? Your t on is still ts by 4. When I say do it for omega equal to 4 omega s, that what I mean is that if I apply the input at 4 omega s, the system is still switching at omega s, right? So if the system switches at omega s, then this remains ts by 4. Correct? So this goes, so this becomes 2 pi. So essentially this becomes 1, this becomes 1. So the numerator and the denominator cancel. You end up with only that 1 by 1 plus j 4 omega s RC. Right? And if 4 omega s, what does it remind you of? If this term does not exist, this big term does not exist, and you are only left with 1 by 1 plus j omega RC. It's like as if the switch didn't play a role. Right? And if the switch does not play a role, it behaves like a low pass filter, which means that there is severe attenuation at 4 omega s. Because by definition, omega s RC is much, much greater than 1. Correct? So now the interesting thing is that if you see that at omega equal to 0, we have good value. I mean, this h of j omega is good. The envelope has a decent value. I mean, in fact, envelope has a value of 1 at omega equal to 0. We saw that at omega equal to omega s, the envelope has a value about 0.9 or so. Similarly, you can do for 2 omega s, 3 omega s, but suddenly at 4 omega s, it goes to like almost severe attenuation. Right? So what happens at 4 omega s, that it suddenly goes to severe attenuation. And again, you will see that at 5 omega s, it is going to have a slightly higher amount of value and so on. 5, 6, 7, you are going to have higher amplitude, and suddenly at 8, again, it will go to 0. I mean, it will have severe attenuation. So it looks like something is happening at multiples of 4, right? And what is 4 here? 4 is n. N, basically the amount of which I have is basically 1 over the duty cycle. Correct? So it looks like something is happening at when the input frequency is equal to multiples of 4, right? Or multiples of n per se, right? Or in other words, if I say in terms of time period, it looks like if the input time period is equal to one time period of the equal to if the full input time period is encapsulated within the on time of the switches, then something is happening, right? In this particular case, this is what? Ts by 4, right? And if omega equal to 4 omega s, input omega equal to 4 omega s means what? The full waveform, the amplitude of the input waveform can fit into Ts by 4. Sorry. The full period of the clock of the input waveform can fit into this Ts by 4. Correct? So it looks like if this condition happens, that the full waveform fits into this Ts by 4, I'm getting severe attenuation, and it feels like it's like a continuous time RC filter. For all other cases, it feels like it's not. But for this particular case, it feels like it's a continuous time RC filter. Yeah, so that's a good question. So let me draw it out. So the answer here was 1 by 1 plus j4 omega s RC, right? Which is approximately equal to 1 by j4 omega s RC. So this is Ts by 4. This is S of t. And when input is at, So let's say input is cosine omega 4 omega st. Okay. So obvious, or let's say sine omega st. It's easier to draw sines. So it will be sinusoid. What will be the period? Yeah, which means? Which is Ts by 4, right? So the period of the input will be, right? And then it will continue, and come here. Again, the same. And it repeats, right? So now think from the perspective of the switched RC filter. So when so what is this capacitor seeing? The capacitor is seeing this full cycle, right? And then 0 at the input, right? Then you close the switch, open the switch, doesn't matter. Input doesn't exist. Then you again close the switch, again it sees. It's almost as if this cycle started from here, isn't it? So it almost seems like it is filtering a continuous time waveform which has a period of Ts by 4, right? So the switch is irrelevant if the switching frequency matches the clocking frequency, or rather or n times the clocking frequency, right? If the switching time period matches the on time, basically. That's what I mean. So if you can encompass the full time period during the on time, then it behaves like a continuous time RC filter, and hence the properties of continuous time RC filter, that very high attenuation at if the RC is much greater than the time period, all those things hold. But for any other frequency, any other harmonic frequency, for example, omega equal to omega s, what was happening? Again, I have not proved this rigorously. Hopefully, we'll have time in the next class to show this. If omega equal to omega s, that is sine omega st, then your period is in this thing, right? So your capacitor waveform, or capacitor rather, is seeing only a quarter of this cycle, right? And then, so let me just draw it this way. It sees this. Then it again sees this quarter, and so on, right? So every time it sees this part. Because every time it sees this part, it operates only on this part every time. It never sees the negative part of the cycle at all. If the capacitor is never exposed to the negative part of the cycle, it can never, the average cannot ever go to 0, right? Because it is always seen a positive part of the cycle every time. So it's almost, I mean, intuitively you can now figure out, it seems like it is always, because it is exposed to this same set of waveforms every time, it will try to find, because its RC time constant is much higher than Ts, it will try to find out the average of this waveform. It will basically integrate something which is equivalent to the average of this waveform, and hence you get a non-zero value which is close to the DC. Now this statement that I made, I have not yet proved it. We will prove it in the next class, but at least intuitively you should be able to appreciate the fact that why, if omega is equal to omega s, you get a substantial amount of voltage across the capacitor, and when omega is equal to 4 times omega s or 8 times omega s, you do not get. Right? Is that part clear? What value you are going to get intuitively, we'll do it later on. We did it rigorously now. With rigorous thing, with rigor, we found out that amplitude will be this. Correct? 2 root 2 over pi. So that amplitude will be this. This is the rigorous analysis. This is correct. But in the next class, what we will try to do is I do not want to write out the same set of bunch of equations every time. Because I do not want to write out the same bunch of equations every time. It's better to have an intuitive way of thinking. So I'm giving you a trailer. The intuitive way of thinking is that you average this. Question? Okay. Okay, fine. Any other questions? Okay. So this, by the way, we have. Okay. So before I move on, we did the. I put I put sine omega naught t here because e power j omega naught t I cannot draw, right? But how do I make? How do I come to, or rather, how do I figure out what will be the actual response of sine omega naught t from the transfer function, or from this expression? Right. So this is a response for e power j omega s, omega s plus delta omega. If I apply e power minus j omega s plus delta omega, what is going to happen? All the j terms will go to negative, right? And then you add them up, right? So, and hence you are going to get the response to cosinusoid. If you subtract, you are going to get a response due to sinusoid. Subtract and divide by 1 by 2j, right? So I leave it up to you. You can do that exercise and then satisfy yourself whether the final output is real or not if you apply cosinusoid and a sinusoid. Okay. Okay. So till now we have done is to find out the magnitude that will be seen across the capacitor at one particular time, t on. Right? What I have done till now is only at t on within the cycle. Right? That does not encompass the entire cycle. So you have to do what happens if I'm sampling it, or if I'm observing it above t on and less below t on also. Right? So again, what we have done is we have figured out if I am looking at the capacitor at particular snapshots of time, which is t on, which is t on plus ts and all, I am going to get the wave. I'm going to get the waveform, which is j omega naught t on times e power j omega naught t. Right? I want to find out for a generic case for all t for this particular system. I want to find out what happens for t on, so t greater than t on and t less than t on. And obviously within the cycle, because if I know everything within the cycle, it will repeat. So let's do the easier one first. Now we already have the framework. I do not want to repeat the same framework every time. I'm going to use those expressions that I have gotten, because there's no point in finding out the expression if I cannot repeat it. Right? So I'm going to repeat it. So let's do for, if I'm observing, again, going back to the thing, observation and application instances. If I'm observing at a t which is greater than t on, right? So this is where I'm observing. Okay. So what should the impulse response look like? Now you should be able to tell me. I want to sketch out the impulse response. If the observation instance is t, which is greater than t on. So t is greater than t on, less than ts. So I'm going to draw the h of t comma tau, where t is greater than t on, less than ts. So what happens at tau equal to 0? h of t comma tau is being drawn with respect to tau. Huh? So which means it will be 0 and it will be 0 till tau equal to this, right? Tau equal to t minus t on, right? So till tau equal to t minus t on, it will be absolutely 0. Then yeah, right. So you will get 1 over RC here, and then the same thing. It will, I drew it for you. Where will it stop? What will be this? No, what will be this interval? T on, right? Okay, very good. And then it is going to repeat, and it's the same thing. Whatever we did till now is going to repeat, right? So which means I should be able to do it easily, correct? Because I know what this waveform is, isn't it? This seems to be this ht of tau seems to be a time shifted version of the expression that we have already, of the Fourier transform of the expression that we have already figured out. Make sense? So which means that this, let me call this h of period t. So this is h of t tau will be h t on tau so basically the time shifted version of, if I call this ht on tau minus t minus t on, right? So I should also have t comma. Right? So which means that your h of j omega t, where t lies between t on and ts, is basically whatever that big expression that we had. I'll just write it from memory. Right? Times e power minus j omega t minus t on. Okay? Make sense? This I just use a property of Fourier, time shifted property of Fourier transform. Okay. Okay. So now the interesting thing is, so this is a function of t. Right? So this is basically some constant times e to the power minus j omega t. Correct? If you think about it, so if this guy can be broken down into e to the power j omega t on times e to the power minus j omega t. And everything here is independent of t. Correct? So I can say h of j omega comma t is basically some constant, and that constant is basically h j omega t on times e to the power j omega naught, or j e to the power j omega t on times e power minus j omega t. Right? Doesn't make sense? Some people are like staring. I'm not sure whether this is. I'm drowning you in algebra, is it? Yeah, unfortunately, I do not yet know how to make it more palatable at this stage. So that's why I'm trying to get with I'm breaking the monotony of the algebra with some intuition. But yeah, let's see. Fine, but I mean, at least this part, do you agree with the fact that if I am observing, if my observation instance is in this period, right? Then the envelope has a function of t, right? And the constant times e power minus j omega t. Now, what is the intuition behind the fact that the envelope is e power minus j omega t? Why should that make sense or not make sense? Think from the perspective of the final output, or the voltage across the capacitor. This is only the envelope. This is not the voltage. What will be the voltage across the capacitor? Yeah, right. So voltage across the capacitor will be multiplied by, so V naught during the off period, j omega t will be this h of j omega t multiplied by e power j omega t, right? So which means it will be equal to h of j omega t on times e to the power j omega t on. That's it. So this is independent of t. Why? Why does it make sense or doesn't make sense? But this is dependent on t on. Excellent. Exactly, right? So the voltage across the capacitor is getting locked to whatever it is seeing at the falling edge. And that is a function of t on. Makes sense. But after that, it should not change. Whatever be the input. Isn't it? So the final output of the capacitor when the switch is off should not depend on the input that is coming after the switch has closed. After the switch has gotten open. But it should depend only on the value of the capacitor at time t equal to t on. And this final expression is basically telling us that it is independent of t after t on, but it is dependent on the value on the capacitor at t on. And that is what we expect intuitively also. Right? Does it make sense? Okay. So we have figured out t on. What we have figured out the response after t on. We have to figure out the response before t on. Okay. Okay. So let's do that. We'll do the same logic that we have done till now. So I'm now interested. I'm applying my observation time t is here. T less than t on greater than 0, right? So then, I mean, I will have all the scenarios between 0 to ts. Okay. So now tell me again, what will be the ht comma tau? So again, I'm observing here. My observation, this is my observing time. So it will start off with 1 over RC, and it's going to exponentially decay till t. Very good. This t. So this value will be 1 by RC e power minus t over RC. Right? Okay, goes here. Then Then 0 for how long will it wait? It's basically it'll wait till here, right? So this interval is how much? This will be, so this interval is Ts minus T on. So this will be Ts minus T on plus T. Correct? Okay. So it will wait till so from here. So this is Ts minus T on plus T. And it will start from here. And then this interval, subsequent intervals will be T on, right? So this is subsequent intervals will be T on, and then so this will be T on. And this everything will be with respect to Ts now. Right? So this interval is Ts. Correct? So this is slightly different from the previous case because the expression that we have is for when it starts off with 1 over RC, and basically the Fourier transform of this guy we know very well, right? This big expression that we have is Fourier transform of this guy. Where it starts over from 1 over RC, and then everything is T on, and this is Ts. This is T on, and so on. Correct. So I have to squeeze this into, you have to use this so that I get the Fourier transform of the previous guy on the top. Right? So what I can do is I can break this top guy into two formats. One is from here. This seems to be a scaled and shifted version of this guy. Right? And then I'm going to find out the Fourier transform of only this guy and add them up. Correct? So the first is, so if I have to show scaling, then I have to move this slightly. So basically H. So I call this guy, let's say P of tau. Okay, so I can basically say H on T comma tau is P of tau plus some H shifted, right? H shift, some alpha times H shift, right, of, let me just call it H shift of tau. So what is H shift of tau? H shift of tau is that H T on comma tau, but scaled by e to the power minus T by RC, okay, times e to the power minus T by RC, and time shifted also, right? So I have to multiply this and then time shift. H T on, time shifted by tau minus Ts minus T1 plus T, right? Ts minus T1 plus T. Okay. And plus P of tau, right? So your P of tau is, P of tau should be simple. I mean, we did this in the last lecture, right? So P of tau is nothing but 1 by RC e to the power minus T over RC U of tau minus U of tau minus T, right? So you get, sorry, this is tau by RC. Should be minus tau by RC, right? Because this discharge is e power minus tau by RC. sorry, this discharge is, this is the initial condition. It is for minus T by RC, the initial condition, but discharge is for minus tau over RC. Okay, so I mean, if we do this, you are going to get the same expression that we got in the previous lecture. So it will be 1 plus j omega RC, which will be because of this, and this will have a time shifted version. So you are going to get 1 minus e to the power minus, no, you are going to get this additional term e to the minus T over RC. Sorry, P of j omega. And you're going to get e to the minus j omega T. Right? And this H shifted, so I should have done the transfer function, Fourier transform this, the above one first. So H shifted version of j omega is basically e power minus T by RC times whatever that, this is the time shift. So I'll just use the time shift first, minus j omega Ts minus T on plus T times H of j omega T on. Correct? So I'm going to, this will be 1 and this will be 1, and we're going to add this up. Okay? Make sense? Again, this is envelope. This is not the final output. For final output, what I'm going to do? So V naught j omega T is basically multiply H shifted version of, or the Pj omega. I'll just multiply with Pj omega T. So, I mean, it's easy to multiply in the denominator. So I'll just write the entire thing of Pj omega. So I'll just write e to the j omega T minus e to the minus T by RC by 1 plus j omega RC times times the top guy. So which is H of j omega T on. This is independent of T times e power minus j omega Ts minus T on, again independent of T. This minus T will get cancelled, right? And then you are going to get e to the power minus T by RC. Okay. So this output is dependent on T. That makes sense, right? Now, the thing that we have to understand is, under the assumption, now we'll invoke some assumptions, like the similar assumptions that we had with RC to be much, much greater than the on time or the time period. Can you comment on this guy? So if RC is much, much greater than Ts and omega equal to omega s. Can I neglect that term? Can I not neglect that term? And mind you, we are again talking about not arbitrary T. T is greater, T is between this. Sorry, T on. Should I retain that guy or should I neglect that guy? Huh?
E to power minus T by RC as 1 minus.
That is, we can write everything, but what about the denominator? Denominator is much, much greater than 1, right? Can the numerator be much, much greater than 1? No, right? So which means the denominator is much, much greater than numerator. So I can basically say that that is 0, isn't it? Well, sorry, this should be not plus, this should be plus, right? So this first term can essentially go to 0. There is some variation, of course, but it essentially says that it almost goes to 0. What about the second term? The second term, I know that this guy is close to 1 at omega equal to omega s, right? And this does not contribute to any amplitude in magnitude. And I get e power minus t over RC. And t is much, I mean, we are talking about t to be between 0 and t on. And t on is much less than RC, which means that is also close to 1. Correct? So what are you saying? Even though there is a time effect of time, it seems like if RC is much greater than TS, long story short, it is almost equal to whatever you are seeing at time t equal to t on. Because this is the guy which is contributing the most. So the sampled value on the capacitor seems to be the key, because it looks like, I mean, that's not looks like beyond the when the switches are off, the voltage across the capacitor will be equal to the sampled value. But it seems like even when the switch is on, it seems like the voltage is almost not changing when the switch is on. It is almost equal to H omega t on, isn't it? At omega equal to omega s. Makes sense or doesn't make sense? If you are not convinced, put a value of t equal to 0. For example, when the switch is just turning on, this goes to 0. This anyway is neglected, right? Omega RC, the denominator is much greater than the numerator, right? If you are again not convinced, just put values. Assume RC to be equal to, assume Fs is equal to 1 gigahertz. That is, omega is like 6 times 1 gig. And assume RC to be equal to, R equal to, let's say, 1 kilo ohm and C equal to 100 picofarads. Right? 1 kilo ohm, 100 picofarad is 10 power minus 9. Kilo times pico is 10 power minus 9 times 100, 10 power minus 7. Omega is 10 power 9 of that order. So 10 power 9 times 10 power minus 7 is of the order of 10 to the 2. So the denominator is of the order of hundreds, like 600 or something. And the numerator is barely around 1. Right? So the first term is basically 1 by 600, 1 by 700, that order. So the first term essentially goes 0.005 or something like that. The second here, at t equal to 0, this is 1. And this I know is about 0.9. Right? At t equal to t on, basically the system is evolving from t equal to 0 to t on. I'm looking at the boundaries. T equal to 0, it looks like equal to hg omega t on. At t on, it is definitely hg omega t on. Right? So it seems like the capacitor voltage is not changing. Once it attains a steady state, it does not change. Right? By the way, we have not, this analysis does not ever tell you how it attains steady state. It is only sinusoidal steady state analysis. Right? Moment you do Fourier transform, we are basically saying, I don't care how it has come to steady state. We are trying to find out what happens at steady state. Right? It seems like at the steady state, all we need to understand, as long as the time constant is much greater than the on time, is what is the value at t on. If we know the value of t on, we are done. That is itself the voltage value across the capacitor. Right? So all this bunch of maths that we did, it is leading us to the point that the most critical thing is find out the voltage value at the sampling instant, or at the falling edge of your capacitor. True only for RC to be much greater than omega s. If it is not, then obviously you cannot neglect this term. If RC is not lesser than, if RC is much lesser than omega TS, right? So then this denominator is closer to 1, right? So then it becomes comparable, right? So that is one of the, some of you will probably do data converters, mixed signal courses sometimes later on. There you will see that the RC time constant is kept to be, R is kept to be as small as possible. Right? You have switches and you keep the R's to be as small as possible. In those cases, you cannot neglect the first term. obviously, right? And in those cases, there is the memory on the capacitor is almost always wiped out because your RC is much, much lesser than 1. Sorry, much, much lesser than T on. So this term is very high. It is for minus exponential, that minus of magnitude will be very large. So this goes off, completely goes off. So when you are doing mixed signal data converters or sampling analysis, this is the term that you bother about. When you are doing these very high RC time constant analysis, this is the term that you bother about. And this is the full term. Okay. So when you have, depending upon what type of scenario you are in, you can choose which is the variable of interest. Okay. Any questions so far? No? Okay, then we'll stop here. I wanted to have some discussion with you guys before we go. No quiz.